Right, welcome back to another chemistry IGCSE video. In today's video, we'll be tackling chapter 6 as per the IGCSE syllabus, that being chemical reactions. Now, this is actually a really big chapter, and I would say it covers three main aspects altogether. The first being physical and chemical changes, which I like to group together with rates of reaction. The second aspect here is reversible reactions, and the third aspect is redox reactions. Now, usually I prefer to, I'm not really sure if this is going to be a large 3-hour video or something, or I might even break this up into 3 separate parts. I really don't know. But we might as well start with the first part of this chapter, which is quite easy, where we'll be looking at physical and chemical changes. Starting with physical changes, some of the characteristics of physical changes are that, number one, no new substances are formed, and which you can actually see through some examples. So, when I mix iron powder with sulfur, I create a mixture of iron powder and sulfur. I don't create a new substance. It might look different from before, but it's still just iron filings that is distributed amongst the sulfur. A similar thing happens if I dissolve sulfur in a solute known as methylbenzene, a solvent known as methylbenzene, and this just creates a solution, but I can still separate the sulfur from the methylbenzene easily. Of course, the solution itself is flammable, so you need to be safe in the lab, but I can easily separate it, which I can also easily separate the first mixture produced in the first example. But that brings me on to the second property of physical changes, which are that they are easy to separate. Now, using the first example, I can demonstrate a very easy and common separation technique, that being magnetic separation. So since iron is ferromagnetic, I can just take a bar magnet, run it through the mixture a couple of times, and I can easily separate the iron powder from the sulfur. If I mix iron filings in the solution of sulfur and methylbenzene, I can simply filter the iron out using a funnel and filtering paper. So as you can see, it's quite easy to separate mixtures or the products of physical changes using physical means. A few other methods of separation include decantation, crystallization, chromatography, but there are obviously many others. Distillation is another common one. And also we'll be looking at, I'm pretty sure, chromatography more in detail. We'll be looking at chromatography more in detail in the last chapter, which has to do with purification. Right, coming on to the second part of this topic, chemical changes. Now, a chemical change is simply a chemical reaction. They are the same things. They mean the same thing. And obviously, when we look at examples, any chemical reaction is a chemical change. The primary or the major property that chemical changes have is that one or more new products are formed, new chemical substances are formed. So in the case with iron and sulfur again, this time rather than just mixing them and creating a mixture, if I heat both of them up, I can actually cause them to react, creating iron 2 sulfide, which is a completely different chemical substance from iron and sulfur on their own, and is different from the mixture of iron and sulfur as well. So that's the first property of chemical changes. Obviously, you can observe this in any chemical reaction, quite evidently. The second property would be that energy is taken in and given out in chemical reactions. If you watched the previous video, you would know that all chemical reactions are either exothermic and endothermic, and all chemical reactions involve energy absorption and energy being released, or bond formation and bond making. Now we come to the third property of chemical changes, which is that they are usually difficult to reverse, at least by physical means. So I can't really use magnetic separation to remove the iron from iron sulfide. That's not how it works. I can't filter out the iron from iron sulfide either. Rather, I'm going to have to do many consecutive separate chemical I'm going to have to carry out several consecutive chemical. As I was saying, you would have to carry out many consecutive chemical reactions to separate the iron and from the iron sulfide, or separate sulfur from the iron sulfide. But it is possible to separate chemical. It is possible to separate the. It is possible to reverse the reaction. It's just more complicated, and you can't really use physical means. And yeah, that's done. Well, we are done with the physical and chemical aspect. Now we can start with rates of reaction. Right, so the second thing that we'll be looking at in this chapter is the rates of reaction or reaction rates. And the rate is just a measure of a change that would happen in a single unit of time. So when we say rate of reaction, we are just talking about the speed at which a chemical reaction occurs. And you can measure the speed in two ways. You can either measure the mass of the reactant that is used per unit time, or you can measure the volume of the product that is formed per unit time. And of course, if you use the second method, then the product whose volume you'll be measuring has to be a gas. And from both of these definitions, you can actually derive a bit of a formula where the rate of reaction or reaction rate is either the mass of the reactant or the volume of the product divided by time. And from this, we can determine that rate of reaction has the following units. It can be measured in kilograms per hour, or you can even use grams per second, or centimeter cube per minute, centimeter cubes per second, etc., etc. It depends on the initial units of your measurements. Now, obviously, there are experimental ways of doing both methods, or carrying out, or you can carry out experiments to measure the rate of reaction using both the methods, but those are different, and we may look at it later on, but it's not really important as per the syllabus. Now, practically speaking, you won't really carry out any experiments here, but you do need to know the basic theory behind how you can use both the methods. So let's take this first method. Let's take an example of magnesium reacting with, let's say, hydrochloric acid, which will of course form magnesium chloride, MgCl2 plus H2, plus H2, yeah, H2. Let's just make sure it's balanced. The reaction is balanced, and if we were to carry out the reaction in a round bottom flask as shown here, with this just being a strip of magnesium, you would see that it releases the hydrogen gas, and we could use something called a gas syringe to measure the volume of gas. So how it works is that as this gas makes its way through the gas syringe, it's going to push this stopper to this side. It's going to push it to this side. And you actually have a bunch of readings here, and let's say this end over here, let's say this end over here ends up here. You could just take the reading at this end, and that would show you the volume of hydrogen that was produced from this reaction. And then you could also, and on the side, you can of course have a stopwatch to measure to measure the time. And yeah, you would stop the stopwatch when effervescence stops, bubbling stops, and that's like a good indicator of figuring out how to use the stopwatch. So that's the first method done, and you can actually represent your values graphically. So let's say at 1 second, 0.2 centimeter cubes of gas had been formed. At 2 seconds, it was 0.4. At 3, 0.6, etc., etc. You can actually draw a graph to represent these values. So let me just draw one real quick. Right, I made a small mistake. This is actually for the second method. You would use a gas syringe for the second method because you're using volume. It's fine. Let me just make a few changes. Right, I've made this necessary changes. So this reaction or this example pertains to the second method where you use volume to measure the rate of reaction. So you use the gas syringe for volume, and then again you would use the stopwatch here, and you would start the stopwatch as soon as you drop in the strip of magnesium and stop it as soon as effervescence finishes. Now let me just draw the general graph of results for the second method where you measure volume against time. Right, so this is the graph for the above experiment. Now you can actually make 4 observations from this graph. Number 1, the rate of reaction, first of it obviously changes all throughout the reaction up until the reaction ends. And it's fastest at the beginning, it's fastest at the beginning, but it gradually decreases. And you can see that it decreases due to this curve right here. So that's the first observation. Number 2, I will say, and this is a trick, the steeper the graph, the greater the rate of reaction tends to be. So if a graph has a curve like this, and you compare it to a graph with a curve like this guy right here has a faster rate of reaction, which is another way you can find out that at the beginning the rate of reaction is greatest. And the point in the graph where the curve goes horizontal actually shows us when the reaction ends. So the reaction actually ends at this point right here. Let's assume it's 5 seconds. So the reaction ends after 5 seconds. Of course, this is just an example. And once the reaction ends, it goes flat because the volume of the gas doesn't change any further, regardless of time. And there are actually 2 ways of calculating the rate of reaction. You can either take the average rate of reaction. So let's say I asked you to calculate the rate of reaction at the average rate of reaction at 5 seconds. You would just take whatever volume of gas is at that point. Let's say it's 20 cm cube, 20. So you could just do 20 over 5, which is 4, and it would be 4 cm cube per second. That's the average rate of reaction. If I asked you to find the actual rate of reaction for the graph as a whole, let's say at this point, right? We'll call this 2 seconds. And I asked you to calculate the actual rate of reaction. You would take a tangent, making sure that this angle and this angle are roughly equal. And you would calculate the gradient along this tangent. For those of you that do physics, you might be familiar with this. But you just calculate the gradient using a tangent. And that's for the actual rate of reaction. And usually your answers, it's going to look a little weird with decimals and whatnot, but that's to be expected. And obviously, the main thing here is to be able to interpret the graph and be familiar with the shape of a graph pertaining to changes in volume as the reaction occurs with time. Right. So that's half of it done. Now we can move on to mass. Again, I'm sorry I made a mistake at the beginning. This example is specifically for the second method. Now let's tackle the first method. Right, so here we have the first we are using the same reaction for the first method as well. Let's say you carry out the experiment and you measure the mass of how the mass of magnesium changes with time. You would obviously use a stopwatch for time or to measure time, and you would use a balance or a weighing scale to measure the mass. The graph looks a little different. It's kind of the previous graph but upside down, where it begins at this point right here, or it begins at the starting mass of the reactants, and it gradually decreases over time until the reaction ends at it ends at the point where the graph begins to go flat. Let's again call this 5 seconds. So after 5 seconds the reaction ends and then it's just flat. There's one very important thing to note here that you can easily see by comparing the two graphs. The graph here begins at the origin because at the beginning of the experiment, before the reaction even begins, there's no hydrogen, and so you're going to see, and so the gas syringe is going to remain as is, so there's no change in the volume of the product. Whereas here it doesn't begin at the origin, which is self-explanatory, but it doesn't even end at the origin. That's because you can't. Even though the magnesium is reducing, at a point the reaction ends and you just have excess magnesium left, which is why it remains constant after the reaction ends. So those are the two graphs. You really need to know how to interpret the two graphs. Again, the steeper the curve, the greater the rate of reaction. And usually at the the rate of reaction is greatest at the beginning of the reaction. Now we'll be looking at some factors that affect the rate of reaction and how they change them. And we'll also be talking about the collision theory alongside it. Right, so here we are going to be looking at some of the factors that cause a change in the rate of reaction. Okay, now here's a trick question. If I ask you for a factor that causes a change in the rate of reaction, simply a change, some of you might say concentration or temperature or surface area. That would be wrong. You have to say change in temperature or change in surface area or change in concentration. Now if I ask you, name a factor that causes an increase in the rate of reaction, you have to say increase in concentration or increase in temperature in order to be correct. So that's just something that you should keep in mind from an examination point of view. Now let's look at the theory of how changes in these factors can cause a change in the reaction rate. So let's say I have a reaction and I increase the temperature, which you would usually do by heating it over a Bunsen burner. This actually causes the reactant particles to have more kinetic energy. So EK represents kinetic energy. And because they have more kinetic energy, they move faster, which can lead to them having more collisions. And each of these collisions will actually have more energy as well. And since more collisions are occurring, the likelihood of effective or successful collisions occurring also increases. An effective collision is just a collision that leads to the formation of new bonds and subsequent the subsequent formation of products. So when more effective collisions occur, the reaction rate also increases. And if I were to reduce temperature, the opposite would happen and the reaction rate would decrease. So that's temperature done. Right, one last thing to take note of here is that generally speaking, an increase of 10 degrees Celsius causes the rate of reaction, let's just call that rate of reaction, to double. So an increase so this is a very general thumb of rule. It may not apply to all reactions, but it's followed generally. Right, so the second factor that we must consider here is change in concentration. So if I were to increase the concentration of the reactants, that would mean that the reactants are occupying a smaller space, which in turn means that the same number of particles are occupying a smaller space. And due to this, the frequency of collisions and effective collisions is going to increase. However, the energy will not increase or decrease. It will remain the same because I'm not really adding or removing energy. I'm just taking the particles and shoving them in a smaller room, in layman's terms. And obviously, because the effective collisions are increasing, the reaction rate also increases. And then by proxy, if I were to do the opposite, decrease concentration, you would say that, the frequency of collision decreases, yada, 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 and the reaction rate also decreases. So that's the change in concentration done. Now let's look at the third factor, change in surface area. So when we say that changing surface area can influence the reaction rate, we're basically talking about which form the reactant is in. So if we use the example of magnesium and hydrochloric acid reacting, if I were to use lumps of magnesium, then the reaction rate will be lower than if I would have used magnesium in a powdered form or a strip of magnesium, which have a greater surface area. So the theory behind this is that when I increase the surface area of reactants, so using them in a powdered form for instance, more particles of that element are exposed to collisions at once. And this causes the frequency of collisions to increase along with the number of effective collisions, and so the reaction rate increases. Again, the energy of the particles still remains constant. EK, or the kinetic energy, doesn't change. It doesn't change. It remains constant. So that's change in surface area. Now let's look at gas pressure. Right. So the fourth and the second last factor affecting the reaction rate is actually gas pressure. So an increase in gas pressure means that the same number of particles, the same number of reactant particles are occupying this a smaller volume, which is just an increase in concentration, which, as we've discussed before, leads to an increase in the rate of reaction. And of course, if you decrease the gas pressure, the opposite would happen. You would decrease the rate of reaction. And now we can move on to the final factor, which is actually the presence of a catalyst. And that's a little different in terms of explanation, but it's still important and it's not that hard. Right, so the presence of a catalyst. Presence. Yeah. So a catalyst is just any substance that can increase the rate of reaction, but it's left unchanged after the reaction, which is to say that the catalyst itself doesn't take part in the reaction. Now there's many examples of catalysts out there. The most prominent examples would be the transition metals or compounds containing the transition metals. You'll learn more about this when we cover metals. Enzymes are another subset of catalysts. Now, enzymes are basically just biological catalysts. So they are still catalysts, but they are essentially proteins that are made by your cells. So all enzymes are catalysts, but not all catalysts are enzymes, which is a funny thing, but it's still true. Right, so here we have a reaction pathway diagram where you have energy at the y-axis and you have the progress, the reaction progress at the x-axis, or the progress of the reaction. Now, the main thing I want to point out here, whether your reaction is exothermic or endothermic, that doesn't matter. You'll notice that there's an activation energy that the reactants must reach before the reaction can actually begin. And what the addition of the catalyst basically does is that it reduces the activation energy that's needed for the reactants in order for the reaction to occur. And this makes it so that the reaction rate is faster. So to summarize, the catalyst lowers the activation energy of a reaction. And this allows reactant particles to use less energy in order to actually break bonds and then create new ones and make subsequent products. And this also means that because the activation energy is lower, the frequency and energy of collisions remains the same, but the number of effective collisions actually increases. So that's just something you should know. You might want to know a bit more about enzymes and where they are used. You use them in biological detergents where things like lipase and protease can be used to clean fat stains and blood stains respectively. The disadvantage of this is that the enzymes can easily denature at high temperatures, so you can't really use them at high temperatures. Aside from this, that should be it for reaction rate or rates of reaction. Let me just take another look at the syllabus. And yeah, it seems that we've discussed everything that you need to know. And I would say that this is part 1 of the chemical reactions video. I'll upload part 2 in a few hours. Right, as always guys, thanks for watching. I hope you at least learned something and took something away from this video. Thank you for watching, and maybe consider subscribing if you really like the video, and I'll see you on the next one.